Okay, let's look at another example, example 4. Let's say this is a block of mass M sitting on the ice dome, which is in the shape of half sphere, and it has a radius of r. The question is, if we give a little push, but still we say initial velocity is near 0, then obviously this block will start to slide down. Initially, it will be able to follow the contour, but you can imagine when this one goes down, the speed will pick up. At a certain point, the speed is so high, it will get airborne, which means normal force equal to 0. The question is, at what angle, with respect to horizontal, that the block will airborne, which means lose contact. Even this lose contact, that mg will always there. So before this position, particular point, we have both mg and fn because there is contact. But at this moment, fn equal to 0. So let's take a look. Since before this point, we have mg and fn. At this point, we only have mg. So the only non-conservative force is Fm. So work done by non-conservative force, summation, there's only one non-conservative force, and that is 0 work, because normal force is perpendicular to the contact surface. If the object moves along the contact surface, ds is tangential, Fn is centrifugal, which means follow the radius direction. So it's perpendicular to each other. Then we say, okay, delta ME equals 0 for the block. Initially, right here, it only has a height. If we take h equals 0 is right here. So initially, it only has gravitational potential of mgr. But right final position, when this one lose contact with, the block lose contact with ice, it has a height of mg. Obviously, this is r, and we want this height that is r of sine alpha. So it's r of sine alpha. Plus, it has speed, 1/2 mv squared. Now, what do we want is this alpha. So if we do not know v, we cannot solve it. But certainly we can solve this problem, because at this moment, if we split mg, we get mg of, this is obviously mg of cosine, it's mg of sine. Why? Because if this one is perpendicular, this is tangential, perpendicular to that one, this is vertical, perpendicular to that one. So the angle right here, this angle is alpha. So this component is mg cosine of alpha. That one point to the center of a circle is mg of sine alpha. If I amplify this picture right now, that point to the center of the circle is mg of sine alpha. And then tangential is mg of cosine alpha. That is the split of two forces. I mean mg. So you only have mg because at this position it lose contact, normal force equals 0. Since that it still has a tangential velocity v and does circular motion about a circle radius r, so we say that the centripetal force is mg of sine alpha. That equals to the block of m and v squared over r. It's responsible. mg sine alpha is responsible to provide the centripetal acceleration. Therefore, we can replace this, if both sides times by r, and then both sides times by r, then we can replace that mgr sine alpha. See, mgr sine alpha. Do we want to replace that? No, I don't think so. Actually, we want to replace the 1/2 mv squared term. So r cancel. Both sides times by 1/2. So we want to replace the 1/2 mv squared term. Therefore, the left side for this equation, mgr, and the first term, mgr sine alpha. The second term, 1/2 mv squared, 1/2 mv squared. This r cancels, see that? And actually is 1/2 mgr sine alpha. So it looks like this is 3/2 mgr sine alpha. So mgr cancels, is 1 equals to 3/2, right? Because mgr, we have mgr everywhere, mgr, 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 and this 1 is left. And then we have 3/2 of sine alpha, and looks good. Sine alpha is 2/3. That's less than 1, because we know the sine value max is 1, so it's good. If we get 3/2, then we're in trouble. But now it's 2/3, then we can solve this alpha. That is the position the block will lose contact with the ice and airborne. Okay, let's look at another problem of just one block system. Okay, we don't have a 2 block connected by a rigid string, but we have 1 block. The case is like this. We have a ground, frictionless here, yes, friction, and frictionless again, and then at the end of it, we have a spring constant K. The block initially is here, and this position that, as a matter of fact, the spring has already been compressed by X meters. So the spring has been compressed, and obviously the spring is not happy, so the spring will exert a force, Kx force, try to push the block away. The block is not being connected with the spring, so it will separate from spring. And then, let's say this is a position of A from here. Position B, position A is here. This is the moment. Position B, let's say, is from here. Position C, let's from between BC, yes, kinetic friction, that's why it would give mu K. And then there is a circular track directly connect here. Our goal is that the question is, how much shall we compress initially? That we want the block, after experience that friction part of the surface, and go up the track and reach this, still does circular motion. So it still has a V right here. Let's name this point, since we have that BC, let's name this is D. So it still has a speed, but it just made it there. So it loses contact with the track, but the gravity again provide the centripetal acceleration to the circular motion. So the question is, initial, obviously if we press really, give a really big initial compression, then when the block and the spring get separated, the block has a high V, and after even past this frictional surface, it still has a high V. If it has a high V here, and then it will be able to certainly reach the top. So it really depends on what is the initial. Okay, so how do we solve this problem? We need to do it in a segment. First of all, let's say from A to B. From A to B, what happened? From A to B, how many forces on the block? Obviously, AB has no friction, and then we have normal force, Fn, and we have mg. So, because displacement is horizontal, normal force doesn't do work. So from AB, we say that mechanical energy ME of A equals to ME of B. So that's that. At A, it has 1/2 of K x initial square, and at B, it has 1/2 mvb squared, because spring has no more, compression anymore. The block leaves the spring, but the block gains kinetic energy. From B to C, however, the situation is, let's draw the block here, say for example, And obviously, when this block moves from B to C, that's the displacement. And kinetic friction Fk is backwards. So it is negative Fk does the work that time the distance from B to C. It's known, say for example, that equals to the change. In this case, the block, the only change of mechanical energy is that 1/2 mvc square turn is less than when it moves slower because it experienced the surface friction. So there's no change of height, so there's no change of gravitational potential energy. And the block left the spring long time ago. So, and we can replace Fk. This is very simple because at this position, as we can see, normal force Fn simply equals to mg. So we can replace this Fk by mg in this case. Okay, this is from B to C. So from A to B, we have that. That is from B to C. That's that. And next one, let's talk about from C to D. From C to D. C, we have speed. Then we go up. Look at the block. When the block moves along the circular path, no friction, and the only force again is normal force and gravity, since that displacement ds is always perpendicular to the normal force, and so there's only one conservative force acting on this. So we can use conservation of mechanical energy again. So we say ME of C equals to ME of D. At C, we have 1/2 mvc squared. At D, it has speed, 1/2 mvd squared. It has height, mg of 2r, because that is 2r above the ground. So with all these equations, what do we do? Well, our question is obviously, what is the initial compression? So that's pretty straightforward. So what we do is we just actually we need to add one more, because at this D, mg is responsible for that circular motion. So mg is the centripetal force provide the centripetal acceleration vd squared over r. So we should replace that mvd squared by mgr. So that is 1/2 mvd squared is mgr plus mg2r. So from here, and we can see we have 3/2 mgr, which is known value. We can express that 1/2 mvc square turn. So then if we know this term, and we can get the VB term. If we know the VB term, we go with it. So eventually, let's list it one more time. That 1/2 kx initial square, that's what we want, equals to 1/2 mvb square. If we want this term move to the left, and that term move to right. So if we want this, we want 1/2 mvc square. 1/2 mvc square term actually is 3/2 mgr. That is the 1/2 mvc, this term. And this term goes to that, and that term is plus of fk, which is mu k mg. Fk is mu k mg time distance vc. That is this term, because this term moved to the right is plus, this term moved to the left. That represent, these two terms represent 1/2 mvc square, and this is the work done by kinetic friction moved to this side. This actually represents 1/2 mvb square, represent this term, that equal to that. So we can solve that initially how much we should compress depending on spring constant K, depending on the circular radius of circular loop, depending on surface condition of mu K, depending on the distance between B and C. Well, that is very interesting. Okay, let's look at another interesting example. That is something that we mentioned in chapter 7. In chapter 7, we have a simple pendulum pivot at the ceiling of length L and a point mass M at the end. Say if we apply a constant force, shouldn't say constant force, a force with constant direction, which is horizontal, but magnitude might change in a way that we move this one, the point mass in the circular path, which means it is always same distance away from, let's name point O, that pivot point. How do we do that? Well, simply we apply force, right? The force we apply, F, it is always in the fashion of that sigma T plus F plus mg equal to 0. That means at any moment that the net force on the object equal to 0. Well, initially the velocity is near 0. So finally, because we learned that W work done by every single force you add it equal to delta KE. If your initial velocity is near 0, if the net force is always 0, then the work done by net force equals 0. So the final, V final here is near 0. Now, our question is, what is the work done by this force? See, the problem is, tension T, first of all, the angle changes, right? Second, the magnitude might change too. So this is in the fashion defined as these three forces add together as a vector equal to 0. Like what? Like tension T is this way, tail tip, and then gravity is tail tip this way, and then this force F is tail tip this way. So T is here, mg is down, F is right here, and this angle alpha is right here. So this is in a way of tail tip, and finally there's no gap, which means this means sigma F equal to 0, which means all the forces add together form a closed vector. This is a triangle. So if one of them always change magnitude and direction, and this one also changes, and how do we find the work done if we just try to follow the definition F dot ds? We don't know what is F, so we cannot solve it. So what we do is we can use that concept of well, net work done is the work done by this plus the work done by that plus the work done by mg, right? That equals to change of kinetic energy, let's say 0 in this case. And since that it's circular path, any movement ds tangential, so we say that T dot ds is TDS cosine 90 all the time, no matter at what location. That is always 0. So it looks like we only need to find out work done by mg, then we can, because this is 0, if we can find out work done by mg and we find the work done by F. Work done by mg is relatively simple because mg is constant, so we just say constant force, total displacement, cosine the angle between them, let's say. So let's take a look at this case. Now, if initially it's here, finally it's there, so isn't that true displacement is that? Right? This is alpha. And the displacement is this direction. And force is this direction. So cosine theta is actually asking for that. This is theta, because that's displacement, that is the force. We know that before we actually had experience. Cosine theta equal to negative cosine gamma. So we can replace this by negative cosine of gamma. And displacement, so let me draw this again. This is the displacement S, and initial position here, final position there. The change of height, this is gamma. Look at this. S cosine gamma actually give us that. That is H. So the height, obviously, from initial to final, it gains height. So what we do is we just have this continue, okay? Equal to mg, right? We'll replace cosine theta by negative cosine gamma. So there's a negative sign in front of it, negative mg. And then S cosine gamma is this delta H. So it's delta H. We just need to figure out what's delta H. What's delta H? Let's take a look. If this is the pivot point of the string, and if this is L, and isn't that true, the change of height is that L minus this much? This much, if we look at this right angle triangle, then we can say delta H actually is L, which is that. Subtract that part is L of cosine alpha. So the change of height actually is L1 minus cosine alpha. Since cosine alpha is always, in this case, is less than 1, so delta H is positive. So the work done by gravity is negative mg delta H. So we can replace here, it's negative mg and delta H. We can replace delta H here. All right, that's delta H. So what it is, since work done by gravity is negative, why negative? Because when an object goes up, the displacement on the y direction is up, gravity is down, so gravity does negative work. If this turns 0, gravity does negative work. If you move this turn to the right, it's positive. So you get what is work done by that variable force, capital F. That's very interesting.